We are discussing about artificial neural network and particularly it is a multi-layered feed-forward neural network that we will be considering, and this particular network will be used to model a classifier. So, let us see how we can model a multi-layered feed-forward neural network. We will be concentrating on a let us model particular neuron of a layer of a particular layer, which means let us consider a jth neuron of ith layer, and say let me denote it by this symbol NEJI. And so, to model this neuron, it has its input weights. So, you consider that a weight is a vector, and as it is connected to all the neurons of the output of all the neurons of previous layers, and if I consider that number of output is given by n I minus 1. So, where n I minus 1 is the number of neurons at I minus 1th layer. So, and the bias is considered as W j 0 I. So, this is the dimension of input to this neuron, which means also the number of neurons in the output layer for a fully connected network. And as I mentioned, dimension of output at the ith layer, which means that is the number of neurons at the ith layer. So, output of the neuron can be described in the mathematical form in this way, that it is considered first to take a net input from the input from its input. That means x I minus 1 is actually the vector generated by I minus 1th layer of dimension n I minus 1. Now, this so you have the product, you have the weighted combination of this input, and then it is added with a biasing term which has been considered here, and then that becomes a net input to the function which will be a nonlinear function which will be generating the output response. So, if I consider the input output relation in the ith layer, then that can be described in this form. You have in the ith layer, you have once again n I number of output neuron. So, for each one there is a weight vector which is connecting all the neurons of the previous layer. So, this is how this relationship can be expressed. As you can see that each input weight vectors, it is multiplied, it is making a weighted sum with respect to the components of the previous layer, and then it is generating the output of the ith layer. So, note that the dimension here is of n I, this output is n I, this is a dimension, and these are the biases. So, we can express in brief, we can denote it that this is the finally this is the weight matrix of at ith layer, and this is corresponding the bias vector at the ith layer. So, these are the two parameters which are related to the ith layer. So, the input output relation can be described in this form, as you can see that in a particular block diagram we have explained here. So, given an input, then from this input layer use these parameters W1, B1 as described, you generate the output for the next layer, and in this way you propagate the output to the end of this output layer, to the input of the output layer, and finally you get this output. And at each layer the description of the parameters is in this form. There is a mistake here, it should be n I as per our description, it should be n I. Similarly, it should be. So, in short, the model can be considered the whole set of parameters. See, all these set of parameters, they define the finally the collection by these symbols parameters, as if it is representing the whole collection of parameters. So, in a model you have the parameters are defining this model, and it has its corresponding input output relation following the following the functions of the neurons as we discussed before. And at each functional block, this is how it is processing the input. So, when you consider an optimization problem, we are trying to model a neural network in such a way that it satisfies the input output specifications, which means that if I give you an input output specifications in the forms of say xi oi, and these are the samples of n samples. So, we have to find out w such that it produces y given input xi for all I. So, this is the problem, optimization problem, and we can use the same gradient descent method to solve this. So, we define a error function which is defined in this form here. You can see that it is considered the sum of mean square error. It is basically mean square error given the output and given the predicted output from the model, which is expressed as f x I w. So, this is a predicted output and this is the actual output. So, the square of this deviation is a single observation, and then average over all these observations will give you the mean square error. So, this error has to be minimized. So, you have to find out that w which minimizes this error. So, once again we can apply the same gradient descent technique. So, that is what we can do here. So, the procedure is similar. We can start with an initial weight w naught, then we update w iteratively. So, it is weight means collection of weights, as we have described that collection of parameters. It considers weights and biases of every layer of the artificial neural network. So, the corresponding update scheme can be shown in this form, because eta I into this. So, eta I takes care of all the scaling factors here, and as we can see that when we are doing derivation of this particular function with respect to w, it will come like this, ok minus this, and then of course, you have to compute the derivation of f, gradient of f with respect to w. And you can apply once again stochastic gradient descent. So, instead of considering the all the samples at a time together, that means instead of considering this sum, we can simply use a single sample like the previously what we have done, and we can immediately update these weights and continue doing for every sample, and finally, when weights are getting converged, that means there are little changes in the values of weights after updation, then we can stop. So, computation of gradient itself is a task that we need to do it here, and here let me first discuss with respect to a single neuron or single perceptron. So, we can apply the chain rule very effectively. So, we know what is a chain rule. Let me explain that. Say this is the corresponding functional description that. So, this is the input here, and you have corresponding weights. So, this is the net input finally after considering weighted combination, then adding the bias term, and then next part is that you have to this becomes an input to a nonlinear function f, and then it produces output O. And your error function, if your target response is t, then error function in this case we consider as t minus O whole square. So, this is a square error that we are considering. So, now if we would like to perform what you need to you are interested here, you need to compute the derivative of E with respect to individual weights, because we are trying to update the weights. So, what is the how this particular response varies, that we need to find out that gradient, and we should move towards or how it is affecting this error. So, we should move towards that direction which will be minimizing the error. So, that is steepest gradient directions. So, how do you compute it? Now, by applying chain rule, what we can do at this part, we can compute delta E, delta O, and then this function, what is delta O? Delta O is nothing but fz. So, here we will be computing delta O by delta z, which means f dash z, and then at any weight Wi, we will be computing delta z by delta Wi. So, which means as you see, this is a weighted combination, it is Wi xi, so it will give you xi. So, delta E delta O, this will give you 2 into t minus O, then f dash z, that depends upon the functional form. We will see a particular function if we take how it looks. So, it should be multiplied with this, and then this should be multiplied with this. So, then that is what is your total delta E delta y. So, it will be 2 into say t minus O, then you have f dash z, and then you have xi. Okay. So, that is how the chain rule is considered. Let me give you the corresponding summary here also. So, we need to compute, as we mentioned, we need to compute all these gradients, and as I was telling you that all these components we have to compute. So, this is this part, this is this part, yeah, it is minus 2 into t minus O. In my note I have written 2 into t minus O, that was an error. So, you just multiply all these 3 things. So, you will get the corresponding delta E delta Wi. Now, let us consider a particular form of fz, right. This is a sigmoid function. So, if I take the derivative with respect to z, it will look like this. Now, incidentally, this can be expressed in this form, and which is nothing but fz into 1 minus fz. So, this is one interesting part, one interesting simplification if you consider only sigmoid function. So, if sigmoid function has this property, and in many cases in neural network sigmoid function is used, and this particular property is effectively used in computation. If I want to compute delta E delta xi, because we will see later on also that in some cases we need to compute that, and then also we can apply chain rule, and the whole thing will be there. The relationship between delta z delta Wi and delta z delta xi is a kind of there is a duality. So, if delta z delta Wi in this case would be xi, similarly delta z delta xi it will be Wi. So, you will find that the expressions could be considered here. The interesting part here is that the whole computation can be done using analytical methods. So, you do not have to do any numerical sense, you do not have to use the numerical simulation to compute. So, sometimes for a complicated function, what we observe that we give a change to the input and we observe the change in the output, and then use the ratio of those changes as a derivative. But in this case, you can directly compute by giving the functional by giving the values at that point. So, only values of x, w or weights and inputs, they will be only required to compute this particular function. So, once you compute the functional value, then you can compute also the derivative using those values only. So, you can compute at a point, that is what is the advantage of this particular method. So, when we are when we would like to compute the gradient of a feed forward network, multilayered feed forward network, we apply the same chain rule, but in this case, since there is a layered computation, now the chain rule has to be also applied following that layered architecture, which means that we should compute from output towards the input. So, you should compute all the derivatives at the from the output end, and then you should proceed towards input and compute successive derivatives. So, which means from output layer to input layer, and we can compute the partial derivatives of weights at I minus 1th layer from the corresponding derivatives of the ith layer. We will see how we can do it. So, let us consider this particular concept here. We would like to compute the derivative with respect to this weight. That means, we would like to compute delta E delta W 3 1 2. You note that here in my notation 2 denotes the layer. So, this is the second layer and 3 denotes the jth neuron of the previous layer. So, this is the third neuron of the previous layer, and here the weight 3 1, it is a connectivity of the third neuron of the previous layer to the first neuron of the second layer. So, previous layer is here. So, that is the notation we are using here. Similarly, these are y's are shown as outputs here. So, actually I have shown all these outputs which are affected by the change of these weights. So, this response is affected by the change of these weights. So, this is generating, this y41 becomes the input to this particular neuron. So, it is acting like an input, but any change of this weight will affect the changes here. So, which means I need to compute here, for example, delta E, delta O, then any change here will affect output. So, I need to compute delta O, delta yt3, that means with respect to this. Similarly, I need to compute the derivative with respect to this. Then there will be, I need to compute this derivative of this with respect to this. So, in between there is a functional block here. So, we will have to consider that. So, in this way we have to compute. So, only these derivatives are to be computed and then we can find out this one. So, here we will see that we are computing delta E, delta O, then delta O, delta y13, delta O, delta yt3, then delta y13, delta y12, delta yt3, delta y12 and delta y12, delta 312. And the relationship is that you have for computing it. So, it is delta E, delta O, and then this delta O, delta y13 and delta y13, delta y12, this plus this into this, because this is getting distributed here. So, this is the relationship with respect to this. And you note that the computation of delta y12 and delta w312 should be f dash z12 and y41. That is the role of this y41 as we have mentioned. So, this is a single neuron, this is the output. So, computation of this y12 this should be f dash. So, this is what is fz. So, f dash this is the net input, z12 is the net input at this point and this is y41. So, we will continue this computation once again. So, it shows at the top, these are the layers 1, 2, 3, 4, 5, these are the layers, and then it is this computation is carried out in this form. So, delta E, delta O, delta y13 and delta O, delta y23 and this one. So, this particular thing, that delta y23, delta y12, which means this part can be computed as the block f dash z23 and w12. So, this is my notation. So, that is what we are considering here. So, this branch we are considering. Similarly, this one is also considered. We will be discussing about a particular simple rule by which the gradients can be propagated from output towards the input direction, and that rule is called delta rule. So, let me explain this particular rule by which can organize the computations very nicely. So, we measure the error as we discussed, that as the square of deviation from the target t to the response given by the network for a particular input and particular values of weights or parameters of that network, which is O. So, t minus O whole square is the error, and we would like to find out, compute the gradient of this error with respect to or derivative of error E with respect to some parameters. For example, in this diagram we are considering the parameter W31. So, you note here in my notation, this is the weight, and you can see this 3 is the third neuron in the previous layer, and 1 is the first neuron of the current layer. So, the previous layer of neuron, this is the first layer, and this is the second layer. So, our convention is that to denote the weight connectivity from the third neuron, output of the third neuron of the previous layer to the current layer is in this form. Similarly, the output of the third neuron of the previous layer, which is the layer 1, is denoted here y31, and also you can see output of the first neuron of layer 2 is denoted in this form. Similarly, output of layer 3, first neuron of layer 3 is denoted here, of layer 3 it is also denoted, that is the second neuron in this form. And finally, this is of course the fourth layer, and only one neuron is there, and fifth layer is just the output response, which is redundant, and we are not denoting with any other symbol other than O. So, this is the convention that we are following, and we are showing all the necessary responses which are affected by the change of weights W31. So, when we compute the gradient gradient of error E with respect to W31, this weight, then these are the variables which will play a role in determining this gradient. So, let us find out how this this gradient value is dependent. So, you can see here we would like to measure this value, and which will give me the corresponding updates of the weight W31 parameter. And so, applying the chain rule. So, first we compute the gradient of E with respect to output O, then gradient of output O with respect to this gradient y1, and then subsequently gradient y12. So, this is that value. Similarly, these two are added here. So, because of the linear operations, this is the other value, and finally, when we are computing the gradient with respect to W31, it is the y12 with respect to W312. So, these are the components which we need to compute, or these expressions which we need to find out given this particular responses at this instance. So, in this case, we have already discussed how to compute the gradient of y13 with respect to y12. Suppose we know the gradient of gradient of output O with respect to y13, and that is we are calling, that is a value delta 1 3. That means, this is the accumulated gradient till this point, till the output of the first neuron of third layer, we denote in this fashion. Similarly, the gradient at this point will be denoted as delta 1 delta 2 So, it is delta 2 3. So, that is the gradient at this point. That is my notation, and that is the definition of delta. So, delta is the accumulated gradient till a output, till the output of certain layer and the corresponding convention of writing delta in this fashion. Similarly, we can write the gradient changes along edges also, particular edges. We will see how we can do it. So, let us expand this particular quantity, that means gradient of y 1 3 with respect to y 1 2. So, let us explain this particular quantity which is the gradient of y 1 3 with respect to y 1 2. So, these are how they are related, since in between you have the corresponding nonlinearity which is f z, and that would play into role. So, we can write it as we can write this fact as say f dash z, and then we know that there is a weight which is also connected here. So, it is, since it is a linear combination of this. So, if this weight as per our convention, it is W, this is the first neuron. So, this is 1 and this is also 1, because this is the first neuron of third layer and this is 3. So, according to our convention, this is the weight. So, this is linearly related. So, this is scaled, y 1 2 is scaled by W 1 1 2, and then it is contributing to the net input, which is again determining the y 1 3. So, we can write delta y 1 3 delta y 1 2 as f dash z, that is also at that point. So, we will see whether we have taken any convention. So, we can write it also, say f dash z 1 and it is layer 3, f dash z 1 3 into W 1 1 then 3. So, this is the expansion. Similarly, we can do this expansion, and later on we will see how the chain rule is defined with respect to this. So, let me proceed. So, this is what as I mentioned we will compute this part, and similarly we will compute the other one, and this will expand. So, as I mentioned, this is expanded into this form and this is expanded into this form, that is coming from here. This one is coming from here and this one is coming from here. Now, we define the delta 1 1 as I was mentioning, delta 1 1, like I have defined earlier, the delta, this is delta 1 3, and at this edge this is delta 1 1 3, and that gets multiplied with W 1 1 3. Similarly, at this stage this is delta 1 2 3, and that gets multiplied with W 1 2 3. So, we'll find out how this is happening. So, this is what is delta 1 1 3, as I have mentioned. This is getting multiplied with W 1 1 3, and this is delta 1 2 3, and this is getting multiplied with W 1 2 3, and that would give me the corresponding here, that would give me delta 1 2. So, this is the delta rule. So, if I write it, so we can define the delta rule in this fashion, as I was mentioning, that delta 1 2. So, this is what? This is delta 1 2 is equal to then. So, this is added, this is equal to the weighted addition of delta 1 1 3 and delta 1 2 3, where the weights are the weights of the corresponding edges. So, that would be more clear when we show it here. So, this is the delta rule. So, once you get delta 1 2, similarly in the same way you can also get the delta value here. So, it means it has to be multiplied with f dash. So, from here it should be multiplied with f dash, it should be z 1 2, and then you are computing actually the response of this point. So, it is delta y 1 2 delta 3 1 2. So, it is this multiplied by f dash z 1 2 into the y 3 1, because when you are computing the gradient at this point, then the multiplication factor with respect to this parameter will be this response. So, that is what we will be getting here. So, you can see that it is delta 1 2 multiplied with f dash z 1 2. So, this is delta 1 2, this is f dash z 1 2 in that path, and then you are multiplying with y 3 1. That would give you this quantity, and which is used for updating this weight. I think this is explaining, this diagram explaining in a clearer way. So, what it is doing, let me explain. So, you compute, as I mentioned, delta 1 I at this point. So, which is the gradient, accumulated gradient value from output to this point. Say this is delta j I. So, in that way you are computing all this accumulated gradient value, and then it is first it is propagated. So, delta k 1 I is multiplied with respect to f dash z. So, this is delta k 1 I. Similarly, delta k j I this. So, you take the weighted sum of all this. So, you take the weighted sum, that gives you the corresponding accumulated gradient value from the output to this point. So, at this point. So, and next it will propagate in this fashion. So, it will again propagate in this fashion, and so the update of weight should be this particular the delta E delta O into this, because it is from the weight output response. So, this is our update. In this way weights are updates are computed at every branch. So, this is what is exactly computing this gradient. So, in this way you are computing the gradient or gradient of with respect to the corresponding weight with respect from the gradient of the error, and that is how we get the gradient vector. And then the algorithm follows in the same fashion, that for each training sample you compute functional values of each neuron in the forward pass, and then update weights of each link starting from the output layer using back propagation, and then it should continue till it converges. One of the things we would like to mention here, that when you are doing artificial using this model, whether it is a classification or regression model. Now, you can see primarily it is a regressor. It builds a model to predict functional value effects given input x, but you can convert this model, you can use this model also as a classifier by appropriate encoding of classes. That means, your output vector would be those encoding of classes. For example, if you have a 2-class problem, you can consider a binary encoding. So, you can consider either 0 or 1, or you can also consider one hot encoding. That means, there are 2 neurons, output neurons, one of them will be 1, other will be 0, for the other class, other will be 0, another is 1. In one hot encoding, idea is that if there are say m classes, that could be represented by m such binary variables, m bits, and only one of them would be 1 for a particular class, rest would be 0. It is necessary that when you design a classifier, you should evaluate a classifier, particularly for a supervised classification problem. So, we will discuss about some methods of evaluation, some measures of evaluation. Consider you have 2 class problems and there are positive and negative classes. Now, there are several possibilities after classification. Like here in this diagram, in this table, I am showing the classification what has been predicted by the model. So, we are saying where it is these are the predicted positive and predicted negative. So, it can predict either positive or negative. So, it could happen that the sample is actually positive and it is also predicting positive, that would give you true positive, or it is negative, but it is predicting positive. So, it is the class of false positive. When it is positive, actually positive, but it is predicting negative, then it is false negative. And in the other way, when it is negative actually, but it is predicting also negative. So, this is a desirable situation, this is true negative. So, this true positive and true negatives are desirable outcomes, those numbers should be high, whereas these two numbers should be less. So, in a measure, we use these numbers, there are different measures, like if I consider accuracy of a classification, we consider what is the total number of predictions which are true, either positive or negative. So, it is true positive plus true negative by total number of samples which have been tested. There are other measures like precision and recall. So, in precision, you see that what is the fraction of predicted positives are true, and recall is what is the fraction of actual positives are true. There are other measures like sensitivity, which is the same as recall. These are used particularly for the medical world. So, or we can consider it also true positive rate. So, it is true positive by actual positive, and specificity is true negative rate, which is true negative by actual negative. And you can combine these scores, two scores, into one F score, which is called harmonic mean of precision and recall. So, which is has been defined here. So, higher the F score, better is the classification when you consider it in combination. For a multi-class problem, we can use a confusion matrix, where once again I have shown here that these are the true classes and these are predicted classes. So, in the diagonal term, if these numbers are high, those are the desirable outcomes. All other terms, there are some kind of errors are there, because it belongs to the actual class omega 1, but your prediction is omega 2 or omega 3. So, the accuracy measure, which will be sum of diagonal by total. There are methods of testing the performance of a classifier. One method is called cross validation, and once again it is applicable for supervised classification. What we do, that we separate training and test data, then we train network using training data and then evaluate using test data. So, for k-fold cross validation, we divide the data in k sets of equal size and we train using k minus 1 sets and test it with the remaining, and we do it for every set as a test set and take the average. So, report the average performance. So, here we come to the end of my talk for particular topic. So, just let me summarize whatever we have discussed under the topic of classification and clustering. So, as we know that classification is the task of assigning a known category or class to an object, whereas clustering is the task of organizing objects into groups whose members are similar in some way. So, clustering techniques, there are several clustering techniques we discussed, like k-means, k-midpoints or Gaussian mixture model. And for classification techniques, we consider naive Bayesian classification scheme, then k nearest neighbor classification scheme, linear discriminant analysis, and finally artificial neural network models. With this, let me stop here, and we will continue for our discussion for our lectures of the next topic. Thank you very much for listening to this talk.